Now we will discuss case 2 when m and m are unequal, that is m is not equal to small m. I mean greatest value not equal to least value. In this case, at least one of them must be different from equal values f of a comma f of b. Say let m is equal to f of c be different from them. The number c being different from a and b and lies within the interval a comma b, I mean in the closed interval a b, and as such it belongs to open interval a comma b. In particular, the derivative of the function limit f dash limit h tends to 0 f of c plus h minus f of c divided by h as h tends to 0 through positive values, it is equal to f dash of c. Also, we know that f of c is the greatest value of the function. So, therefore, f of c plus h is less than or equal to f of c as h is positive or negative values. Say when h is greater than 0, f dash of value is equal to f of c plus h minus f of c divided by h as numerator is negative and denominator is positive. Negative by positive, it is becomes negative. That means the ratio f of s c plus h minus f of c divided by h is less than or equal to 0. Similarly, when h is less than 0, f dash of c value is greater than or equal to 0 as it is explained in the screen. Therefore, what we have got from this is two result is from 3 and 4 f dash of c is less than or equal to 0 when h tends to positive side or positive value and f dash of c is greater than or equal to 0 when h is negative value, and this is for a given function, this is not possible at a time, and if it is possible for a particular point at a particular point at a time is only when f dash of c is equal to 0, which concludes the statement of Rolle's theorem. To supportive to this here, we will try to understand the concept of Rolle's theorem by geometrically. See, I have sketched some graph here. You will observe that as I have told you, greatest value is equal to least value. In this case, the function reduces to a constant function. See that in example A, I have explained it is a constant function graph, it is a straight line. Here you will observe that greatest value is equal to least value. Therefore, the line is parallel to x-axis. If the line is parallel to x-axis, its slope is 0. In that case, f dash of c is equal to 0. In the example 2, B, I have sketched the function y is equal to f of x. I have drawn a tangent at a particular point C. Now observe that slope of the tangent, that you know that f dash of c, which is parallel to x-axis, as you know that the slope of x-axis is equal to 0. Therefore, f dash of c is also equal to 0. Hence, in this case also Rolle's theorem is proved. Now, in the example C, where greatest value not equal to least value, case 2 as I have discussed there, see the function attains the highest value, greatest value at C1 and least value says it is C2 in the interval a comma b. At the point C1, you have drawn a tangent at that particular point. Once again, it is parallel to x-axis, slope of x-axis is 0, f dash is 0. Again at another point C2, you have drawn a tangent, there also slope is equal to 0, hence Rolle's theorem is justified. Similarly, in the case D, it attains the least, function attains the least value. There also you have drawn the tangent here at C in the interval AB. Here also f dash of C is equal to 0. So, in both the cases, when it is a constant m, constant function m not equal to m and m is equal to m, Rolle's theorem is justified. So, now another case, say I have given it as note 2. In the note 2, see Rolle's theorem may not holds good for a function which does not satisfy any of its condition. See, consider an example here, y equal to f of x, say mod x, in the interval minus 1 comma 1. The function is, as you know that mod x is continuous function, as I have sketched that function there itself, and also observe that f of minus 1 value mod minus 1 is equal to plus 1 and b is equal to 1, mod 1 is equal to 1. So, they are equal, second condition is also holds good. Let me discuss in the next class. Thank you.